NanoHub U, online instruction.
Hey everyone, welcome to lecture 420. Here we're going to talk about thermophotovoltaics in more detail. We just developed them in the last lecture, and we essentially said thermophotovoltaics are a way to convert heat into electricity using a photovoltaic cell. And we had very optimistic predictions that you could get about 50% in conversion efficiencies using reasonable temperatures. And now we're going to try to validate this whole model. So first of all, we need validation of our experiment that was the world record. And so here is basically showing, first of all, what is the spectral performance as a function of wavelength over a very broad range of wavelengths. You can actually see that there is a filter which is superimposed on the system, which actually reflects all the way from about 2.5 microns all the way out to about 16 microns. That allows us to recycle a very broad range of wavelengths back to the emitter cell. And then the net result of that sort of photon recycling is that when you add this filtering, the efficiency actually can go up at a temperature of the emitter about 870 from about 16% up to about 20%. So that represents a significant value of this photon recycling if you're in the appropriate geometry, so that it's very likely that photons that are sent to the receiver and are not absorbed can actually be received back by the emitter. Okay, so then that shows that actually that kind of approach allows you to have a big boost in efficiency over the whole range. And so then that's how we get up to about 23% efficiency at about 1050 C. Of course, this model only focuses on radiative power conversion. And so if you have to worry about other losses, such as conduction and convection in the system, then of course the actual efficiency would be lowered accordingly. And so that was encompassed by the enthalpic term that I had in the last lecture for the efficiency calculation. But that does give you some idea. And so again, similarly to what was shown in the last slide, we can show that the efficiency of the emission for a black body, say if it emits like this, and then you add like a perfect step function, then the efficiency would more than double, actually, like if you had a perfect photon recycling factor, to about 90.4% radiative transfer efficiency. Now, this is not like a system efficiency, but it just says like that initial step of transferring energy is very efficient. So the only question you may have is why isn't it 100? And so actually the reason is because there is some like thermalization at relatively high temperatures, especially where you have emission of photons that have almost too much energy, which is then lost in the photovoltaic cell. And then if you try to combine a black body with what's called a Rougate filter, which is a very high performance filter and has been demonstrated this year in Nature Energy by a group from MIT, then you can actually get more than a doubling of efficiency. So it's not quite as high as the 90% from the perfect step function, but it is kind of approaching the performance. But you still do have this residual background on the order of 5% emission, or absorption, if you will, at those longer wavelengths. But it can extend over a very broad range of wavelengths, as was shown in that previous experiment. So that kind of set the stage for this. And then you can also create 1D selective layered emitters that have good selectivity in the mid-infrared. And so this is basically showing as you go from a temperature of 820 degrees up to 1020 degrees that the spectral emission will increase very rapidly at wavelengths around 2 microns, but then at the same time at longer wavelengths from about 2.5 up to at least 6.5 microns as measured in FTIR, then you have a much more modest increase in emission, which is consistent with having kind of these two regimes. And this is obviously a very simple structure. This is depicting this schematically, just alternating silicon and silicon dioxide. And then this is actually the picture of the structure that we made in order to demonstrate this. And so this was published in Proceedings in National Academy of Sciences in 2013. And then there was another paper from the year before, also in the same journal, showing you can also create these 2D photonic crystal structures instead of the 1D structure. And these can also have very high selectivity. This showing like what it looks like on the kind of the micro scale. These individual holes are probably 1 micron across, period is about 1.5. And then if you zoom out a little bit, you can see it's very well ordered. But then if you look at it like on the macro scale, so this is just a photograph, then you can actually see that it's very colorful. Because it has all these periodic structures and it changes color depending on the angle, which is a sign of periodic structure. And then if you look at the emissivity or the absorption as a function of wavelength, you can see it's actually fairly absorptive in this range in the near infrared, and then it drops actually a lot as you go to longer wavelengths. And so then, of course, once we had the room temperature pictures and measurement, then we want to drive this up to high temperatures. And so what we see is that, first of all, if you just had a flat tungsten as a control, then it kind of looks like this at a temperature of around 1233 Kelvin. And then the dotted line is just showing the simulation. So you have a good match to our simulated expectations. But then as you add this photonic crystal structure in 2D, then you can see that there's a big boost in the emissivity at these short wavelengths. But then at long wavelengths, it's only increased a small amount. And in particular, if you compare it to blackbody, you can see that you've actually approached the blackbody limit at 1230 Kelvin, right? Which is consistent with the temperature that we were measuring the flat tungsten. And so, of course, we never expected the flat tungsten to be close to blackbody, but this new photonic crystal is actually very close. But past about 2 microns, then it drops off very rapidly. And so if we have a PV receiver with a band gap around 2 microns, then this is ideal. And then just as another demonstration of the validity of our system model, then if we actually extend the system further to not just include the emitter and receiver, but also include the heat input and then the final measured electrical output on the y-axis. And then input power is basically actually like some sort of fuel, like burning a small chain hydrocarbon like propane. Then you actually start to see, without any kind of selective emitter, then the data points, which are blue dots, actually can be closely matched to the model, which has no fitting parameters, which is good validation. It's all just using experimentally measured component data. So this shows that system model works, and then you can see that for a 1D photonic crystal that's fully optimized, that you have a big boost in output power, which is on the order of maybe 75% increase. So in the next lecture, we'll say, given these kind of results that we've obtained so far, what are the next steps in this research?